We've looked at transverse waves and longitudinal waves. We've looked at wave velocity. We've looked at reflection briefly, and we've looked at interference, okay, when two waves are trying to occupy the same medium and how they interact. And the way they interact we call superposition. Now we're going to look at a very interesting application of interference and reflection, and it's called standing waves. Standing waves are when two continuous waves are moving in opposite directions in a medium, and they have the same frequency and the same wavelength, and they interfere with each other in a really interesting pattern. Here is a continuous wave, transverse wave, coming to a fixed boundary, and it will reflect and it will produce a resultant wave that does something really interesting. So let's look just at the two waves. So you have wave energy going to the right, that's the red, and reflected wave energy coming back. So if these were separate media, they would just look like they're passing each other. But the way they interfere is very interesting because they go between points here. If you look at that, this would be constructive interference. So at that time, it would be constructive interference. Then somewhere in between, and then destructive interference. They're 180 degrees out of phase. So these two things here, these two different approaches, being completely in phase and constructive interference being completely out of phase and destructive interference, result in going between, I'm not sure the resulting standing wave, there we go, between going to a really big resultant wave, constructive in both directions, and basically nothing with them where they cancel out. Excuse me. So if you watch the resulting standing wave only, this is what you would see. You wouldn't see those individual things on there, the individual wave energies that contribute to this. But this is a standing wave. And you've probably seen this in, you could make this in a rope or a spring. You've probably seen this, but it's going much faster in general in real life. Let's look at the parts. We have two parts. One is called a node. A node is the part that doesn't move. That's because it's always destructive interference there. Let me show you. It's always going to be destructive interference. Just the way these geometries work is the red and the blue waves will always have opposite displacements at that point. So that's the node. The antinode is the point where it vibrates back and forth with the greatest maximum constructive interference. Now it's destructive, but now it's maximum constructive interference. So these nodes are the points that don't move because it's destructive interference, and the antinodes are the points that seem to be going back and forth. Notice, here is one complete wave length. So from one node to the second antinode would be one complete wave. So it's a half node, a half wavelength between two nodes, two adjacent nodes. So every one of these, and when we draw them, we generally draw them almost like loops. Each one of those loops is a half wavelength. The distance between nodes, and in fact the distance between antinodes, is one half wavelength. So we use that an awful lot to help solve problems involving standing waves. So when we draw standing waves, we tend to draw them kind of as how you visualize them when you kind of squint. You see it moving back and forth so much. So here would be an example of how a standing wave might look to us. okay? And this isn't an art class. If you drew it like this and this and this, that would be fine. But I want you to notice that these are fixed ends. These are nodes here, nodes, the parts that don't move. Antinodes are the parts that do move. And notice also that this spring can't be both places at once. So this isn't a snapshot of how this looks. This is kind of a blurred time-lapse photography of it. And in fact, this is moving back and forth between there. So it really would be at all these different places over time. It's just vibrating back and forth. If I took a snapshot at one time, it might look like that. If I took a snapshot at another time, it might look like that. If I took a snapshot at another time, it might look like that. Okay, so it's constantly vibrating back and forth. Just because we draw it like this doesn't mean it actually is two places at once. It just can't really happen. Okay, so let's talk about some of the terminology. We talked about nodes and antinodes, but one of the ways we distinguish between different standing waves is by what's called the harmonics. And the harmonics really correspond to just how many of those loops there are in a given string. So let's say we've got a string with a string length L. Okay? And let's say it has a velocity, that waves travel on it with a velocity v. The first, here are 2 points that the string's attached to. If we vibrate it back and forth, if we add energy to it, it's going to have several resonances. And the first one would look like that, just kind of going back and forth like that. And that's called the first harmonic. And we sometimes call that the fundamental harmonic. So that's what it looks like. How wide is that? Well, this, remember, between adjacent nodes, it's a half wavelength. So this distance is lambda over 2. So if we know the string length, we can figure out the wavelength. If we can figure out the wavelength and we know v, we can figure out the frequency, and we'll do a little bit of that. The next one, if I vibrate it, I add energy at higher and higher frequencies, eventually it'll resonate again. And what will it look like? It'll look like that. And that's the second harmonic. Okay, and I want you to notice that there are 2 half wavelengths. So that is the wavelength. If I drew a wave over the top of that, that's one complete wave. Notice this is not one complete wave. That's just either the top or the bottom or something in the middle there. It's half of the, so you have half wavelength, a half wavelength, you end up with a full wavelength. So let me write these over here. If you understand that this is sometimes called the fundamental, I'll just write first, second, third. In the lab, with a vibrating string, we've gotten up to 10 harmonics. Okay, so the third harmonic would look like this. Okay. And notice 2 nodes here, 3 nodes here, 1, 2, 3, 4 nodes there, 3 antinodes. There are 3 of these chunks that are half wavelength each. Half wavelength here, half wavelength here. If I drew it better, it'd be half wavelength here. So this is 3 half wavelengths. So this allows us to start talking about things like frequency and wavelength and velocity to relate those things. So here, 1 half wavelength equals L. So the wavelength would be twice the string length. Here, 2 half wavelengths equals L. So lambda equals L. Here, 3 half wavelengths equals L. So lambda equals 2/3 L. So if we know the string length and we know what harmonic is going on there, we can figure out what the wavelength would be. In general, if you look at this pattern, right, this is one half wavelength, 3 half wavelengths. In the nth harmonic, it would be n lambda over 2s equals L. So lambda equals 2L over n, where n is the harmonic number. Okay. Now, look at that. So if we have these things, we can figure out the frequencies. Frequency equals V lambda, right? I'm sorry, V equals frequency times lambda. So this frequency would be V, the velocity. And again, that's a characteristic of how fast waves will travel. It's a characteristic of the tension and the density of that string. So that V, if we're adding different kinds of energy to this, different harmonics might set up, but the velocity remains the same. The velocity is a characteristic of the medium. Just like in sound, it doesn't matter how high or low I sing a note, it all travels at the speed of sound. Let's say 340, 346 meters per second. So whatever the velocity on that string is, divide by 2L, divide by the wavelength, and you've got the frequency. And we sometimes write 1, 2, we write a subscript pertaining to the harmonic that we're talking about. So the second harmonic is going to be V divided by L. And the third harmonic is going to be V divided by this lambda, which ends up being 3 2L. And Fn would be V divided by this whole thing, which is the same as multiplying it. If you look at this, let's put them all over 2L. Okay? I'm just showing that you can really easily figure out what the frequency is if you know the wavelength and the velocity, and if you know the harmonic and the velocity. But you can see these are all multiples. It's always going to be a multiple of the fundamental frequency. So if I know the fundamental frequency is 8 hertz, well, the 20th harmonic would be 20 times 8, 160 hertz would be the frequency of that higher harmonic, of that 20th harmonic. Okay, so how do we solve problems? It's not too bad. If I say, and I like to pick third harmonic a lot just because it's interesting to do, interesting to look at. A third harmonic on a string has a wavelength of 6 meters. What's the string length? And if the velocity is, I don't know, 20 meters per second, what's the frequency of that third harmonic? And then we put a little 3. We don't always do that, but what the heck. Okay, first thing is when you're doing the standing waves, it's really useful to draw them. Third harmonic, 3 loops. Okay, so there we go. And I know the wavelength is 6 meters. Okay, that's one wave, that's 6 meters. That means a half wavelength is 3 meters. That means the string length is 3 half wavelengths, 9 meters. The way to do that in an equation, okay, it's the third harmonic wavelength. So 3 half wavelengths equals L. So 3 times the lambda was 6 equals L. And then L equals 9 meters. So now we know the string length. Now let's figure out that frequency. Well, wavelength is 6. V is 20. 20 divided by 6, which is 10 divided by 3, which is 3.3 bar hertz. Okay? That's one type of problem you could have. How about a different type of problem? Let's just do the third harmonic again, just because it's easy for me to draw. Third harmonic on I'll just go 12 meter string, and V equals, let's go 20 again, 20 meters per second, and find F and lambda. Okay, well, once again, 3 half wavelengths equals 12. So 24 divided by 3, lambda is 8 meters. Conceptually, if we look at this as 12 meters, well, each one of those loops is going to be 4 meters, 4 meters, 4 meters. So one full wavelength would be 8 meters. So now we got wavelength. V equals 20, lambda equals 8, V equals F lambda. So we have 20 equals F times 8. So we have 2.5 hertz is the third frequency, the third harmonic frequency. Now, let's do one other thing. What is the frequency of the 20th harmonic? To do that looks like a hard problem. Yeah, you could draw 20, right? You could draw 20 of those loops. But an easier way to do it is this. Remember, the 20th harmonic is a multiple of that fundamental frequency. It's 20 times the fundamental frequency. Well, this is 3 times, right? The third harmonic is 2.5. That means the first harmonic, the fundamental, would be 2.5 divided by 3. Really wish I'd picked a different number. But so if that's my fundamental frequency, this would be 20 times my fundamental frequency. So it would be 50 divided by 3. I'm doing something wrong. Nope, I think that's right. 50 divided by 3, which is, I'm not sure what that is, in hertz. Okay. So that'll be, what, 16.6 bar hertz. See how easy that is? Now I've got that, I can find the wavelength of the 20th harmonic. So really, with these standing waves on strings with the 2 ends anchored, it's really not that bad. Okay? Key information is that every harmonic corresponds to a distance between, however many of that distance between the antinodes, or excuse me, the nodes. Okay, so the third harmonic, I'm going to have lambda over 2 between 2 nodes, lambda over 2 between 2 nodes, lambda over 2 between 2 nodes. The geometry ends up being pretty easy. And if I just kind of draw, this is another way of drawing these things. Okay, so same number of loops, same number of internode distances as the number of the harmonic. That helps you set up the geometry. And that's just V equals F lambda. And the little secret, frequency of the nth harmonic is n times the frequency of the first harmonic.